A rainy day here on the Central Coast, and uh, like I said, it's an atmospheric river. I guess they all are nowadays. But all right, what do you expect? Um, what? Oh, I forgot to turn the lights off. So what we got here is homework was due yesterday. Quiz was yesterday. I'll post up the lab. I think post up the lab for this week, and we will go from there. I'll get homework two posted up probably later today, and it'll start with the heat transfer stuff that we've just started talking about, and probably I don't think it'll be due quite next week, but probably the beginning of the following week, because next week we'll finish off some of the heat transfer stuff and we'll move into some of the second law stuff. So we'll see how we go. Let me just quickly shut the lights out so we can get less glare. All right, so now we're ready to roll. We've got, all right, wait a sec. We've got glare over here too. Okay, hopefully we are, yeah, that looks a little better. Okay, just trying to get a little bit less glare on the whiteboard. So homework two will post up later. We do remember that you've got PLC 2 to do this week by Friday, and homework two will post later. Yeah, probably later tonight. And lab two will run tomorrow as usual, and you can do that when you're ready. So I hope that you are all keeping dry and accident free, as the weather is it was quite windy last night, so hopefully things are okay. I know that there are a couple of trees down throughout the county, so hopefully everything's okay where you are. Let's continue talking about heat transfer. We were talking about conduction. So we will continue with that. Now I was kind of trying to motivate the idea behind conduction by giving a couple of examples of what do you think it might depend on, and I was trying to draw some parallels between heat conduction with electrical conduction. Okay, so in electricity, and those of you who've had 4B, and I don't know how many of those of you who are through 4B already, but we're going to find a very similar situation with heat conduction versus electrical conduction. Okay, so what I was motivating last time, I drew you this picture of a hot bath over here connected to a cold bath. Maybe this is an ice water bath over here, and this is a boiling water or something, some hot type of thing. And I connected it with a pipe um, like this. And we just want to think about the transport of heat from the hot to the cold, which, of course, you know is going to run this way. And if we have, this is where some 4B concepts will be useful. If we have something flowing through an area, now if I slice this and I showed you the cross-sectional area, maybe it's circular or something like that, or square, whatever it is. There's a cross-section through which the conduction is happening, right? The dq dt is happening through the cross-sectional area of the pipe. So if I took that flow and I made it per area, then we have essentially what's called a flux. It's a flow of, I don't want to say necessarily movement. In this case, it kind of is a movement, but it's an energy that goes through an area. So you might think of it as like if you have a fan, if you set up just like a regular fan and it's blowing air, you might take a piece of paper or something, and you might say, well, I'm gonna, or this thing here, you might say, well, I want to make this thing move, and if it's gonna if I want to think about the maximum flux of air hitting this thing, then I would have it oriented completely perpendicular to the flow. This would do nothing if the flow of air is parallel with it, like this. So the idea of flux is kind of that something's moving through an area. Okay. And this is a 4B concept also that we use with electric and magnetic fields. But nonetheless, in this case, we actually have energy flowing through the pipe. And it's also, if you cut the pipe and you look at the cross-sectional area, right? If I cut it right here and I slice it, maybe it's a circle. No, well, that's not a very good circle. Maybe it's a circular cross-section like this. And if I thought of which way is the energy going, it's probably coming out. If I take the pipe and I look at it this way, the energy is coming towards me, which would mean that I need to define a vector that's perpendicular to the area of the cross-sectional area of the pipe. And that means a bit hard to draw in this case, but if I kind of flatten it out, then it would be going like that. And I'll call that the normal n hat vector, which is essentially pointed this way from hot to cold. And then what I can then do is basically set up a vector relationship. The flux that I have, right, is left to right in this case, and we call that 1 over a by dq by dt n hat. And that's going to be related to the, remember, it's material dependent, so it's the conductivity of the material. And that is it's a capital K or it's a kappa, whichever one. It's supposedly the Greek letter kappa. It's the conductivity of the material, and it's multiplied by the gradient of the temperature. And if you're not familiar with the gradient, it basically means it's like a slope, but it's, as you can see, it's a vector. So it's a directed slope. It tells you which way is the steepest way up, more or less, and how much up it's going. Problem being, though, if you're careful and you're thinking about the directions, notice that the heat flow, okay, is left to right here, but the gradient would be right to left, okay, because the gradient is telling you the steepest increase, right? It's telling you the direction of the steep, or it's pointed in the direction of the steepest increase, and it's telling you the steepest increase. So really, the other thing I need to do here is throw a minus on there, because the gradient is opposite the direction that the stuff is going, the stuff being the energy flow. All right. Now I've got something that I can balance by saying I've got a flux of energy flowing down the pipe, and I've got a reason for why it's doing that, right? The material is able to transport heat, and there is a gradient in the temperature, meaning that it makes it possible for the heat to actually flow. Now, for those of you who have the cold sensation of a very tight knot in your stomach over having to calculate a gradient, worry no more, we will be approximating it. So let's talk about how to do that now. Effectively, okay, just by way of think about this is the heat flow. And it's not only, it's the rate of heat flow, and this A is the cross-sectional area. Okay. So let's see, I think I got everything. The n hat is just a unit vector telling us a direction down the pipe of the heat flow. So that doesn't really matter because it's going to go away really soon. What I'm going to do is I'm going to rearrange this. So I'm basically solving for what dq dt is. And by the way, I'm also going to rename that. The heat flow rate is essentially a rate of energy, and a rate of energy is a power. Okay, so this is essentially the power um, that's conducted, right? It's conducted power. All right, so we'll just call this, I'm just going to call this P conducted, P conductive. Now, in order to denote that this is a not a momentum and it's not a pressure, okay? Pressure, I would have used the foot on the P. If for power, what I'll do in order to denote that it's a power, I'll use a double bar leg here. So I'll just put another leg here so that it looks like a power. Okay. The temperature gradient, what we're going to do for that is we're going to set up that it's approximately, okay, it's in the steady state. It's approximately related to the difference in the temperatures and how far, right? It's like I told you the gradient is like a slope. Well, it's how much the temperature changes divided by how much it changes it spatially, like how far does it have to go? So the temperature gradient here for a steady state flow is going to be something like delta T. But notice this is not a change, it's a difference. Okay, so we got to be really careful with thinking about how delta T is used here. It's not that we're worried about a change in the cold or the hot temperatures. We're actually just taking the difference of these two because we're assuming these are basically maintained, right? The temperatures are not actually changing, but there is a difference. Okay, so this is the difference divided by L, which is the length of the rod. Right, so this is T hot minus T cold, and it's not a difference in those. It's not a change in those temperatures, I should say. It is a difference in the temperatures. All right, so now we've got the conducted power, we've got the cross-sectional area, we've got the temperature gradient. Let's just rearrange everything so it looks a little bit nicer. We'll go for nicer. And I started off badly because I don't like how I wrote that power. All right, so the conducted power is basically my dq dt. I'm going to throw the area over onto the other side here. There's going to be the conductivity. So we're going to get kappa times A divided by L multiplied by the temperature difference T hot to T cold. All right. Now, note this is not a vector equation, so we're not worried about directionality. In terms of a negative sign in here, you'd say, well, what happened to the minus sign up there? Well, I kind of took care of it by rearranging this thing here. Okay, T hot minus T cold kind of takes the minus into account because the gradient would have been pointed this way, whereas the heat flow would be pointed that way. If there's heat flow, we know it's hot to cold. So it's kind of like it's kind of like drawing the friction of a sliding object, right? You know, if the thing's moving that way, then the friction's pointed this way, and you just know it's pointed that way. So same idea here. This then is our working equation for the conducted heat through conducted heat through a material. So let's take a look at an example of this using a window. And I set up a situation where we have a very cold, maybe a winter's night, and a nice warm temperature on the inside of the house. So we have heat conducted through the window glass. And let's take a look at what that is. and what that looks like. All right, now I'm gonna use this example and we're gonna have a few 4B connections. And if you haven't had 4B, that's okay, don't worry about it. Maybe when you get into 4B, go, oh, look, it's a 4C connection. Um, what we have here is a window, okay, like so. And it's got some thickness to it. This is a little bit of a wonky window here, but I guess it's about, it's not level, but that's okay. It's at least parallel. Well, I've got some thickness to the window, right? Because window glass has some thickness to it. And we'll suppose that on this side here, we're on the inside. So we'll say the inside temperature is maybe say 25 centigrade. And we'll say the outside temperature is say -5 centigrade. Nice sub-freezing night, to which you are probably not accustomed. But let me tell you, it's cold. All right, so right away I can see that heat's going to be going through the window pane this way. Okay, I've got my hot to cold flow. I'm going to be able to calculate what the heat flow is, and based on the temperatures. And I'm going to need to also know a few other things in order to get to that. What I'm going to do, okay, starting with this, my P conduction, kappa A divided by L times delta T. What I'm going to do with this is I'm actually going to find the power conducted per area. Like I'm going to go back to the flux idea. And we're just going to look at how much power is conducted in some type of glass per area, right? And then you'd say, oh, well, if I have a, you know, meter square window, all I got to do is multiply by 1. All right, no problems. All right, so really what I'm going to look to do is swing the area back underneath the power, and I'm going to calculate kappa over L multiplying by the temperature here, the temperature difference here, in order to find that. And this is a common practice just to get an idea of how much something conducts. So we'll go P conducted divided by A equaling kappa over L delta T. And so a couple of things we need. We need, number one, the conductivity of glass, and then we need the thickness of the glass. This is the thickness of a window pane. I assumed it was about 3 millimeters. So let's say that's about 3 millimeters. And I went and looked up the thermal conductivity of glass. And what was that? Beautiful. That is 1. Great. That's 1. So it's 1. This is the thermal conductivity of glass. Now, what units is this thing going to have? Is a question that you might ask. And if you didn't, you should. Because it's going to inform us as to what kind of units we need to use for the rest of the things. So if I'm looking at power, now power is a rate of energy transfer. So that's going to be in joules per second, typically, which would be a watt. And we're keeping things in SI, so this would be in square meters. So the left side of this is going to be watts per square meter. That's a power per area. This is a flux. Over here, I'm going to have a temperature. I'm going to have and by the way, this temperature is again a difference. So you note that if I have a 30 centigrade temperature difference, that's the same as a 30 Kelvin temperature difference. So the use of Kelvin or centigrade here would be fine. This is in meters, or some like the SI standard would be in meters. And so this thing is going to have to be in some confluence, which gives us what we're looking for. That means K of glass is equal to 1, and it's actually exactly equal to 1.0 for window glass. And since I have a meter down here and I need another one over here, that means I'm going to have a watt per meter centigrade or meter Kelvin, if you'd like. That would work too. You could put Kelvin up here. So that means on this side, I'm going to get a watt. The centigrades are going to cancel out. I'm going to get another meter to go with this one here. And that's going to give me watts per square meter. And that's what I needed on the left side. So happy days. With a 3 millimeter thickness, we can go ahead and calculate what the power flux looks like. P conducted per area is going to be this number, 1 watt per meter Kelvin or watt per meter centigrade, divided by 0.003 meters. All right, that's the kappa over L, and now my delta T was 30 centigrades. So this looks like a fairly large number because I'm dividing by the thousandth here, and this is just 1, so it's really 30 divided by 30 times 10 to the fourth. So this is basically 10,000. This is 10 kilowatts per square meter. That's a lot. If you think about the effective, and this is not by any means anything other than an average. If you think about the effective amount of solar radiation hitting the surface of Earth, I think you'd find that about 10 times less than this. So I guess this is a lot of loss for a window glass of 3 millimeters. Now you could say, well, wait a minute, I'm going to thicken the glass. Maybe the glass is thicker. Okay, so maybe it's twice as thick or something. So you'll cut this in half, but it's still 5,000 watts per square meter. So that's a pretty quick loss here. So let's just chain this onto something else for funsies, and then I want to come back to this and show something else about windows and conduction. So let's suppose that I have a 1 square meter window in this room. Well, I've got more than that. Actually, we could make a quick estimate here. We'd go about 3, maybe we go 8, 10, 30? No. Why not? 10, and let's go with about 20. All right, so I'm looking at the classroom here and I'm just trying to estimate how much glass am I seeing in square meters and about how big the room is. So let's assume that here in the classroom, in my classroom here, I'm going to go, that's probably about 2 square meters. That's probably about 1, 2, that's about 6. So I got to get, all right, 2 plus about 6 plus another 2 plus another 6. Okay. So what's this? This is 8 and 8, so that's 16. So this is about 16. Well, that's not about. So let's say this is approximately. In this classroom, say let's approximately about 16 square meters worth of glass. And I know that it's not -5 centigrade outside, but suppose that it was. In addition to all this rain, it's -5 centigrade. Good stuff. Let's suppose that the classroom has a volume of what was I going to say? About 10 by 20, 10 meters by 20 meters by 3 meters. So the volume of the classroom is 600 cubic meters. So how much air is in this classroom? Okay. The density of air is a little over a kilogram per cubic meter. So let's say about a kilogram. It's not quite a kilogram and a half. It's a little less than that. But I don't really want to go too far. So let's just say it's about 600 kilograms worth. Let's see. I need one number that I don't know off the top of my head. So let's just see if I can find it. Yeah, it's about 1 kilojoule. Okay. So what I thought was, all right, let's suppose that we're losing heat through our 16 square meters. All right, I'm saying it's -5 centigrade outside. We'll suppose that I'm losing 10,000 watts per square meter. I've got 16 square meters. All right, so I'm losing kind of a lot. 16,000, 16 times 160,000. Let's go with for time. So this is by rate. Q, or no, I should say power, total power. Power conducted is now that number times 16. So it's 16 times 10 to the fourth watts. And how quickly is this cooling the room down? I've got 600 kilograms of air in here, and I just looked up the specific heat of air. Air specific heat is about a kilojoule per kilogram. So it's 1 joule. It's about 1,000. So it's about 1,000 joules per kilogram centigrade. 1,000 joules per kilogram centigrade, whereas water is 4,000, a little over 4,000 joules per kilogram. So what's the rate of temperature drop in the room? Okay, you might ask that. So you might say, well, okay, I've got a specific heat here. I kind of want to come back to this picture, but I will draw it again. So that's what we're going to do. Okay, so now I'm going to take the, how fast is the temperature dropping? All right, if I'm looking at this, I could say I got like a basically a Q equals MC delta T problem, but it's by rate. So this has become, instead of Q, this is now a power. And this is MC. And now delta T has also become a rate. So we might say it's delta T, the temperature, divided by delta T, the time, right? The rate of temperature change, or if you like, d by dt of capital T. Something like that, okay? So you're wondering how fast is the temperature dropping? Well, I'm going to say it's the conducted power divided by MC, and we just calculated what MC is. So this is 16 times 10 to the fourth watts, and it's divided by, what's the mass in here? 600 kilograms times 1,000 joules per kilogram centigrade. So this will come out okay. So my 1,000 goes away with the three of those. So I got 160 on the top and I got 600 on the bottom. Oh, it's not very quick. It's about 160 over 600. So it's 16, and that's about 2 1/3. If it was 16/6, so this is about 2 1/3, which would have been about 0.6. So if I take that away and that away, it's 16/60. Yeah, so this is about 0.25 centigrades kick up to the top per second. If it was 15, it'd make it easier. So, so it's dropping about a quarter of a centigrade per second at the rate of this. Now you know that the conductive heat is not going to stay constant here, because if I now drop the temperature in here, then that affects what this number is, right? Now, if outside it's still -5 centigrade outside, but now instead of being 25 in here, it's 24.75. Now I've dropped this number a little bit, and therefore this number's dropped a little bit. And I'm going to conduct a little bit less. But anyways, a little bit of fun. Just taking two things and linking them together. What I want to do now is take a look at what happens if I replace all my windows with the double pane windows. All right. So let's take a look at that. My glass, we still know that. And we're going to take this and we're now going to double pane windows. All right, so same situation, 25 inside, -5 outside. And I'm going to have a thickness here of glass and a thickness here of glass. Okay, and I'm going to encase the whole thing like this, and now this is air. It has an air gap in the middle of it, right? So I'm looking at it in a cross section as if I had the window oriented this way. And T out is over here. Okay, so with the same temperature difference, now what happens? Well, now we have multiple conducting objects, right? So let's suppose that I have approximately the same, maybe it's a slightly thinner glass, okay? We have maybe, say, instead of 3 mm glass, maybe I got 2 mm glass. That's not really realistic, is it? Let's stick with 3 mm glass. So this is 3 mm glass on either side, and let's put a 3 mm air gap in the middle between them. So how do we deal with this? All right, well, remember that the conducted power per area was kappa over L times delta T. So now you might say, well, hold on a sec. I'm changing, right? My delta T is going to be different from I'd be T inside to the first pane of glass here. That's going to be some time. Do I need to solve for that temperature? No. What we're going to do is we're going to do a trick. We are going to pretend that this is an electrical problem. And electrically, you do exactly the same thing as what we're about to do here. Now, check it out. If I think about this equation and I think about electrical, the electrical analog to this is that I have a battery and a resistor, and I'm trying to pump current through the resistor, okay? So there's a thing that we have that's called Ohm's rule that relates those two things, where I have a battery voltage, a current, and a resistance. And that's exactly what we have here. It's just a little bit harder to see. The current, all right, is like the conducted power. That's the thing that's moving, okay? The temperature gradient is the thing that's driving the heat transfer, just like the voltage is the thing that drives the current through a circuit. So the delta T and the delta V are about the same thing. If I rewrite it, whatever's left over must be R. the resistance, okay? So let's take a look here. If I rewrite this and I say delta T equals, okay, I'm going to throw all that stuff down here into the denominator. I'm going to have P conducted, right, as my current. This is the thing that's moving, multiplied by the resistance. And the resistance, if I just take this thing and move it into the bottom here, or if I flip it up, I'm going to have L over A. L divided by A, and where's kappa going to be? Kappa is going to be down in the bottom, down here, like that. Okay, so that thing right there is essentially the resistance of the material to thermal flow. If you've had 4B, which I kind of am on a little bit of a talk towards you folks, you might remember that the resistance of a material is the resistivity times L divided by A. Well, happy days, because 1 over this conductivity is the resistivity. So that would be equal to rho times L over A, and that's exactly how you find the resistance of electrically of a material. Nonetheless, what we're going to do is we're going to employ what's called a series connection, right? So in other words, I want to force current through one thing, then another thing, then another thing. So this heat has to go through glass, then through air, then through glass before it comes out. That means the resistance, the total resistance of the thing, is the sum of all of the individual resistors. And each one of these basically acts like a thermal resistor. So I'm going to add them and say I have a total resistance, and then I can just use these two things with the total resistance and calculate what the total power through my series resistor object is here. All right. Okay, so we're going to say series resistors here means that we add resistances. And the resistances are these things right there. All right. So R, if I take the sum, if I take the sum of the resistances, then I'm going to take the sum of L divided by A divided by kappa for each one of these things. So that's going to be L divided by A kappa for, and I'm going to evaluate this at window pane number 1. So this will be window 1. I'll call it W1 plus L divided by A kappa evaluated through air. That's the air gap, plus L divided by A kappa for window number 2. Okay. Now, in this case, what I'm going to do is I'm going to make window 1 and window 2 the exact same thing. And that means I just get twice one of them. And I have to add in the air gap. Okay, so my total resistance should be twice L over A kappa for a window plus L over A kappa for air. All right. All I have to do now is look back over here, and I'm going to take that quantity and I'm going to divide the temperature difference by it, and then I'll have the power conducted. Okay. So I'm gonna factor the area out of this. Okay, so I'm gonna say the resistance is 1 divided by A times twice L over K, 2 L over kappas. Now let's suppose that for windows I went with the 3 millimeter glass, so my L is going to be 0.003 for this meters, and I'm dividing by the kappa for glass, which is 1 watt per meter centigrade. Right? So that number is basically L divided by kappa, and there's 2 of them. Okay. And it turns out it doesn't matter the order. They're just series. You got to go through one, you got to go through the next, you got to go through the last, and it backs up until you reach a steady state. So L over kappa for the glass, what did I say is a 3 millimeter gap for the glass? So 0.003 for the glass, I'm sorry, for the air, divided by kappa for air. And kappa for air, air is a much worse conductor than glass. And it's so much worse that it is 0.026 watts per meter centigrade, which is 1/40th. It's a 40 times worse conductor than glass, which is pretty impressive. Okay. So if we calculate all this, we're going to get some number from this, right? But that's basically our effective resistance. And then we're going to use that in the conductor here, equal to delta T divided by R. Yep. Where the R total, okay, like that. And R total is 1 over A, like this, times all of this stuff in parentheses. Whatever this number is. Okay. Now, prior to this, I was calculating the power conducted per area. So if I do the same thing, you'll notice that this factor of the area is going to go away. In other words, if I want to find the power conducted per area, I'm just going to divide this by the area, which means I have to divide this side by the area, but that puts an area down here in the denominator, and that cancels this 1 over the area that's right here. Okay, so those are going to go away, and I just have this number right here. Okay, so ultimately, my conducted power per area is then going to be the 25 minus 5, which is the 30 centigrade again. I'm sorry, the 25 minus -5. Okay, divided by this number, which I don't know what this number is. So maybe let's take a quick look here. This is, if I take the 0.003 out, this is a number that's 2. Let's just make a quick estimate here. 003 times 2 plus, that's basically 1/40th. So let's just say it's about 40. So that's appropriately enough, 42 times 0.003, which is 1,000. So I'm going to take the 1,000 up here and I'm going to cancel the 3, multiply that by 1,000, get rid of that 3. And it's going to be 10,000 and it's going to be divided by 42. So I've cut this. Oh, it was over there. I've cut that rate of temperature loss by a factor of 40, essentially, here, right? It's 10 to the 4th divided by a number which is about 42 watts per square meter. So I've cut it by quite a bit. And thus the use of the double pane window. It's energy saving, so you don't have to pump quite as much heat into your house in order to have it remain at 25 centigrade. And this means that you have a lower energy bill. So happy days for that, huh? All righty, so that is conduction. Let's take a look at convection. Convection is, like I was saying yesterday, bulk fluid movement, and it's the idea that hot rises, or that heat rises, and it's basically hot air or hot water or something which is less dense. Excuse me. It's less dense than its surroundings, so it experiences some buoyancy. All right, so what we'll do here is we'll examine this, and this was first looked at by Newton. This was first looked at by Newton, and it was his kind of his idea, his attempt at explaining how something cools. Let's suppose that we have a hot object in air. Bulk fluid, what am I saying here? Bulk fluid movement? Eh. and that transports heat. So let's suppose that I have a hot I've got a hot piece of metal here on a, well, I'm not going to touch it. So I got it on some type of hook. I can pull it around and say, hey, look at this. Hot metal, and it's in air. Let's suppose that the hot metal has temperature T. Um, and it starts at a temperature T naught and drops down to a lower temperature. So it's going to start at a temperature T naught, is its hottest temperature. Starting temperature. And then it's going to come down to a lower temperature. And this is the temperature as a function of time. Surrounding this thing is air. The surrounding air temperature is, say, TA, or T surroundings, or T environment, or something like that. So what's happening is the heat is leaving this metal block. It's heating up the air around it. The air around it is going, oh, I'm warmer, I'm less dense, and it's going to start rising. Okay. So let's try and set something up as to what the rate of temperature change of the metal is going to be, because I'm going to assume that the air is not going to change significantly in temperature. This is the idea of the reservoir. When we did the heat conduction, I said we have a T hot and we have a T cold, and we're kind of assuming that those are not changing. Now, if you think about the conduction of heat from the inside through the glass to the outside, yes, the temperature inside would be dropping, the temperature outside would be going up. But these things are so big, right? The temperature outside is not going to be changed that much by your loss of heat through windows. Okay. Your temperature inside will be, but suppose you have a pump that's connected and it's keeping it at that temperature. So the same idea here. I have a essentially infinite, or right, it's big enough that when the heat comes off the metal and it goes into the air, the temperature of the air doesn't change. Right? So it's the idea of a heat reservoir. In this case, what we're going to do is we're going to talk about the rate of change of the temperature of the object. So that means I'm talking about d capital T, d little t. This is the rate of change of the object temperature with respect to time. Right? The rate of change of it, right? So what's going to happen is, how quickly is this thing going to be going down? Well, just like I showed you with the previous example where I came up with a rate of temperature change in the room, right? Compared to, not compared to, but due to the loss of conducted heat through the windows, right? I'm going to get a dt by d little t here of the object because it's losing its heat. And what's that going to be based on? Well, if the object had the same temperature as the air, there's no heat transfer. There's no change in the temperature. Okay. The warmer the object is, the more quickly its temperature is going to drop, right? Because it's going to give off the heat more quickly as it's at a higher temperature compared to its environment. Okay. So this dt by d little t here should be proportional to leave a little bit of room because we're going to have something right in here. This should be proportional to the difference in the temperature of the object as a function of time and the air temperature that surrounds it, the environment temperature. Let's see, this coming up. Well, it doesn't seem like it's dark enough. I'm gonna re-up my pen here. All right. Hopefully that makes sense. The temperature should drop. If it's a higher temperature, it should drop quicker. Okay. All right. Okay. Hopefully that will help. This is the temperature of the object minus the temperature of the air. So the difference, once again, just like a conducted power, like we just saw, it's the difference. In here is going to be a characteristic. I have a temperature here and a temperature here, but I need a time because I got a time over here. I'm going to need a time over here. So what I'm going to do is I'm going to say that there's a time involved here, which I'm going to call tau. And it's a characteristic time, and I'll talk about what that means in a minute. And there's one other thing that we need, which is what is this rate of temperature change? If this rate is positive, then isn't the temperature going up? But it shouldn't be. It should be going down. So the other thing I need is a minus in front of all this in order to ensure that the heat is leaving the hot object. So the temperature of the hot object is decreasing in temperature. The temperature of the hot object is decreasing. All right. And this thing here, this differential equation, is essentially what's called Newton's law of cooling. Okay. And it's a model of what happens when you have a hot object in fluid. And it turns out it's a reasonably good model. Now, if we set about trying to figure out how to find the temperature as a function of time, well, I've got a dt over there and I've got a t over here. That means I got to swap this thing all under there. And I got to take the t over here and break this thing all up so I can rearrange to integrate. All right. So what I have to do is rearrange this to integrate. And what I'm going to do is I'm going to take this parentheses term here, I'm going to chuck it down there, and the dt is going to come over and operate on this 1 over t here. So what I'm going to get is dt divided by t minus t air equal to minus 1 over tau dt. Okay. If I integrate up both sides here, I think you can see on the left side, I'm going to have a log. If you just do a substitution, you'd see that the air temperature doesn't matter. It's a constant, so it's not going to affect the integration. I'm going to get a log of t minus t air on the left side, and I'm going to get a standard temperature. Just a t on the right side here. All right. So, what we have then, I'm going to have to make a little bit of room here. So what we're going to have here then is that I'm going to integrate these two. Okay, that's a constant. That's a constant characteristic time. So that can come out of the integration. I want to throw some limits on here just so we can get a good imagination of what's happening. I'm going to go 0 to t for the time. Now 0 meaning it was hot, right? It started off at its hot temperature and it eventually dropped to some lower temperature. So that means at t0, at time 0, it was at t naught. And some later time, it's going to be at some other t up here. Okay. So when I get the log, I'm going to get the log on this side of t minus ta, and I have to evaluate that at t and at t naught and then subtract the two. So what I'm going to get is, I'm going to get t minus t air here minus the log of t naught minus t air here on the left side, And on the right side, I should just get a delta T or a T or something like that, whatever you might like. T over tau. Okay. Now I have a difference in logs, which means I basically have the ratio of the logs. So this thing here is basically the denominator. And I have to e both sides of it in order to get rid of the log. So what I'm going to end up with is if I rearrange the log such that this becomes the denominator of the entire log, I then exponentiate both sides and then multiply by this thing on both sides, and that will solve me for this. What I end up getting then is that it's the air temperature plus, now I have to multiply by this thing, T naught minus T air, like that, times E to the minus T over tau, like so. Okay, so this thing here is known as Newton's law of cooling. It describes the temperature of the hot object as whatever the air temperature is, because it's never going to get less than that, and an exponentially decreasing rate based on what its initial temperature was. Okay, so if we were to say graph this, what would it look like? Well, that's unfortunate. I should have put that somewhere else, shouldn't I? Okay, hold on. Okay, T as a function of T. And what's it going to do? Well, it's going to start here, right? And it's going to go like that. Well, hopefully reaching maybe not quite that bad. It's going to go more like that, where this is T air. There we go. And this top piece here is where it starts, T naught, like that. Or if you wanted to graph the change in the temperature of the object, then you could start it at T naught minus T air and drop it down to 0. Either way will work. All right. I thought it'd be interesting to look at maybe a hot cup of coffee or something that's been, you know, right? You boil the tea or coffee and make it and you just leave it out. And you say, well, if it's a hot temperature initially, about how much time does it take to reach some other temperature? I just have a quick note about the tau, this tau number here. I think maybe now you can kind of see what it is. It's the amount of time it takes for the change in temperature to reach 37% or 1 over E of its original value. Right, so tau is the time for the difference in temperature to reach 1 or delta T naught over E. Now, what does this mean? What it means is when I'm talking about delta T, if I'm talking about delta T, what I've done is I've subtracted TA over onto this side, right? And I've left it like this, T minus T air. That's a delta T, which is T minus T air, is equal to delta T naught, which is what it was initially minus the air temperature, E to the minus T over tau. So this tau is the time after which the actual difference in temperature is 1 over E of the original difference in temperature. Okay. So if you think of the difference in temperature between the hot object and the air, that difference is getting smaller and smaller and will soon be zero. Okay, so if I were to graph the delta T on this thing, it would reach zero because ultimately the difference between the object and air will eventually become zero, and it will have started at delta T naught, and tau is basically the half-life of that. Okay. So let's take a look at doing an example with this. Let's take a look at doing an example with this with hot coffee or hot tea, because I don't drink coffee. So let's go hot tea. And let's suppose that hot tea starts at 95 centigrade. You've just poured it out of the kettle, and it's not quite boiling, but it's pretty close to boiling. So let's assume that we've got 95 centigrade tea, and the room temperature in a room at 20 centigrade, and that's the air temperature here. That's the air temperature around the tea. Let's say after 1 minute, it's dropped 5 centigrade. It's now down to 90. So at what point does it reach 65? All righty. So the first thing we need to do here, we've got plenty of data. The first thing we need to do here is figure out if we're going to use the Newton's law of cooling expression, I need the tau, right? I need to somehow solve for the tau. So that's going to be our first job. Okay. Once I solve for tau, then after that, notice I'm looking for time. So we're going to have to do a little bit of rearrangements of the exponential equation in order to figure out what's going on here. So first thing is to solve for tau. The time constant. All right. I'm going to start off with that equation that I just wrote, which was the delta T as delta T naught times e to the minus t over tau. Okay, where delta T is the temperature of the object minus the air temperature, right? This is the actual temperature of the object minus air temperature. And delta T naught is the original temperature of the object minus air temperature. Okay, so just to recall that, this is T minus T air, and this thing is T naught minus T air. Okay. If I'm going to solve, and we know these things, right? If I started it at 95, that's T naught, and I know that the room's at 20. I know that 1 minute later, it's at 90. So notice that for 1 minute, for a time of 1 minute, I have all of these quantities. This is going to be 90, that's going to be 20, this is 95, and that's 20. So for 1 minute, I have all of those after 1 minute. Problem is solving this thing for tau. So that means I got to log both sides and whip it all around so that I can figure out where the tau comes out. So what we're going to have to do here is solve for tau. Okay, so let's see what we can do here. First thing I need to do is just pop this thing underneath here. So I'm going to get a ratio of the delta temperatures. I'm then going to log that to get rid of the E. And that means then I'm going to have to flip-flop them to get the tau from underneath to the numerator on the other side. That means I'm going to swap that with the log of the other thing. So this ultimately means that I'm going to get something that looks like this. Minus t divided by the log, let's put that minus up here, minus t divided by the log of this thing over this thing. Okay, like so. That seem about right? That goes there. I get the log. That goes up, that goes down. Yeah, it seems pretty straightforward. So for this, I have everything. Okay. I could do this in minutes. I probably would do this in minutes because to get to 65, it's going to be more time. So I might as well just do it in minutes. I'll take 1 minute and I'll divide by delta t, which is going to be 70 degrees, 90 minus 20. And I'm going to take that and divide that by delta t naught, which is 75, and take the log of that. Okay, so this thing's going to equal negative 1 minute divided by the log of 70 over 75. Okay, and that's called good because that log is going to be a negative number. That's a log of a number less than 1. That's a negative. So that's going to take out this minus sign here, and it's going to pop the 1 minute to be a greater number. Let's see. Did I actually figure out what this number is? Yes, I did. It's 14.5 minutes. For those of you keeping track at home, once you have this, now all we really want to do is ask the question, when does the temperature of the tea reach 65? So I can just operate straight off of this thing and bring all that stuff over to the tau side and solve for what the t is going to be. All right, so t for the t is now going to be negative. I'm going to pop this thing over to that side and multiply tau times the log of delta t over delta t naught. Like this. Now with a 14.5 minute half-life for the t, I'm going to do the same thing, but now I've got delta t at 65 minus 20, whereas my delta t naught is still 95 minus 20. Okay. I've got minus 14.5 minutes, multiplying the log of 65 minus 20, which is 45, and this thing's 75, like so. And that turns out to be a number which I got at 7.4 minutes. Right, again, this is a log of a number less than 1, so it's going to kill the minus sign, and it's going to be a small number which reduces the 14.5. So there you go. All right, so that's convection, bulk movement. Really, we don't talk about the fluid. Notice this is an empirical kind of law that describes the temperature of something hot in and surrounded by something that's cool. You might ask the question, well, what if I had something cool surrounded by an environment that was really hot? What would happen? All right. We don't actually get into the fluid movement itself. We just describe the temperature of the object particularly. Okay, last thing here that I'm going to at least set up so that we can talk about this, and we might roll over onto Tuesday for this. But now we are going to talk about radiation, right? Our last method of heat transfer is radiation. And if you recall from yesterday, everything above 0 Kelvin radiates in the electromagnetic. So typical things that are around room temperature are in the infrared, right? So we are in the infrared, Earth is in the infrared. Most of the stuff that's at normal temperatures is infrared. If it gets hot enough, then it's going to start glowing. And anytime you have flame or a combustion of some type or a nuclear reaction of some type and it heats the thing up, it's going to get to a point where it will probably glow. And you can watch the transition go from a lower temperature, which is red, orange, to a higher temperature, which is yellow, green, to a much higher temperature, which is blue. Which is why it's sometimes confusing to have red and blue marked on the not on the taps, because red is cooler than blue if you're talking about radiation. But I guess because flame versus ice, I don't know, it's a different blue. All right, let's talk about convection. So this is electromagnetic radiation emitted by any object above 0 Kelvin. And you'd say, well, wait a second. By any slash every object, it's any object above 0 Kelvin, which I'll just write as absolute zero. That's going to be better. You'd say, wait a sec, then. That means everything's radiating energy. So why isn't everything just getting colder? Everything's getting colder. If it's radiating energy, it's losing energy. It's getting colder. How is, like if I put my hand on the pen here, I know that it's at some temperature and it's losing energy via radiation. Well, how come it's just staying the same temperature then? I'm not detecting that it's dropping in temperature. So what's going on? Well, remember though that it's surrounded by other objects that are at a similar temperature, right? For example, there's a pen right here, and this pen is radiating, and this pen is radiating, and these pens exchange radiation. This one emits something, and this one gobbles it up, and then it spits it back out, and it hits this one. So there's a thermal equilibrium established by the radiation, at least here, because everything's at nearly the same temperature, right? Except, well, we're a little warmer. Our skin temperature is a little warmer than the surroundings. So we are ultimately giving off more. But then you'd say, well, how come we're not freezing? That's because we eat. So there's that too. We take in energy and consume it. Um, so this is quantified by the Stefan-Boltzmann law. And this comes into the realm of the black body radiation. Okay. This is like what's called black body radiation. This is a whole nother story, which we will possibly get to later. But it's a fascinating story. Remember when I said thermodynamics, you could pick a system. What if the system you picked was radiation? Well, that's what Boltzmann did. He picked radiation and tried to figure stuff out. And then so did Planck, and so did Stefan, and so did these other people. So they actually figured the thermodynamics of the radiation field. So if you plot something like the intensity of the emitted radiation versus maybe something like frequency, which I'm going to have to go lowercase here, I guess. So higher frequency is going to be blues over here, lower frequency is going to be reds. So you'll find something that kind of goes like, it's a characteristic type of black body curve, and the curve is for a particular temperature. For a temperature which I'll just call T1. What if I have a lower temperature? Well, then it looks like this. This is for a temperature which is less than T1. What if I have a temperature that's greater than T1? Well, then it looks like this. Temperature greater than T1, right? So it shifts the peak of the frequency. Where is the peak, right? The peak intensity, I should say. At what frequency does the peak intensity happen? Well, that changes based on your temperature, right? So if you are hotter, then your frequency is higher. If you are cooler, then your frequency is lower and you're down more in the reds, right? So this is more IR down here. And then you get Roy G. Biv here. And you might get UV over here. Okay, so something like that. Ultimately, right now, I have to pause this and we will pick this up on Tuesday of next week. But we'll talk a little bit more about radiation, and we'll do a fascinating calculation involving what would happen and how long would it be before you died if you were ejected into outer space with no spacesuit. So stay tuned for that. That'll happen on Tuesday. Um, in that case, then it looks like we're wrapping up class for this week. Keep an eye out for the lab posting out tomorrow. It's going to be on the Newton's law of cooling, and we'll go from there. So, oh, and keep a lookout for homework two. That'll be up at some point. I think today. That's what I'm guessing. I'm going to go for that. All right. Happy whatever. Happy weekend. Happy till I see you next time, I guess. Ciao, folks.